All right, we're going to work on section 10.6b, areas of polar curves. So we're going to start off by looking at our xy axis, which could also be called our polar axis. Theta equals pi over 2 for the y-axis. But let's say we have some curve. We're going to call this f of theta. Now I want to find the area between the curve and the pole. So let's imagine this little piece over here on the left, and we're going to calculate it from some angle alpha to some angle beta. And I want to find the area of the region. Now we're going to imagine that this section is split up into infinitely small little pieces. Each one of these pieces in here, if you'll imagine, looks like a little triangle. So I'm going to just draw one of them, but I'm going to have to draw it a little bit big so that you guys can see it and imagine it. And if I were to find the area of this piece, it's a triangular section, so that the area of the triangle, 1/2 base times height, where this is your base and the height is the distance from the pole to the curve. Instead of base and height, now let's try and think of it in terms of our function. So the base would be our function itself, f of theta, and the height is r. Imagine that we're going to have infinitely many of these little triangles that we're going to sum up, be the integral from alpha to beta of 1/2 f of theta times r. What are the increments of change in terms of these little triangles? Because the angle is what's changing. It's going to be d theta. F equals to r because that's our function. So that means we have our area formula is equal to the integral from alpha to beta of 1/2 r squared d theta. Example 1, I want us to find the area enclosed by r equals 2 times 1 plus cosine theta. So this is a question that you're given. This function has first order of cosines in it. So that means it's symmetric top and bottom. This, if I multiply it out, is 2 plus 2 cosine theta, which I know to be a cardioid. Your theta interval is going to be from 0 to 2 pi. So when you plug in 0, cosine of 0 is 1. So 2 times 2 plus 1 makes it 4. So your graph has to touch the axis here at 4. Now what happens when theta is pi? Cosine of pi is -1, so then I get 0. So I know that my graph has to look like this. Because our graph is starting and stopping in the same spot, we are going to use symmetry to help us evaluate this. I'm going to say that my area is 2 times the integral from 0 to pi. When we're sketching from 0 to pi, we're adding up the area between the pole and the curve, and this piece that I've highlighted now in gray, this is quadrant 1's area. So this is from 0 to pi over 2. When we continue on from pi over 2 to pi, we kind of get this little section over here. You can double that since top and bottom are the same. And we're now going to plug in our 1/2 r squared d theta. So that is 1/2 r squared. So 2 times 1 plus cosine theta squared d theta. So simplifying this a little bit will give me the integral from 0 to pi of 4 times 1 plus 2 cosine theta plus cosine squared theta d theta. I'm not going to deal with the integration right now. I'm going to go ahead and just tell you that your answer is supposed to be 6 pi square units. Okay, example 2. I want to find the area enclosed by r equals 2 times 1 plus sine theta. So at sine pi over 2, I have 1, so 1 plus 1 is 2 times 2 makes it 4. And at sine 3 pi over 2, I get -1, so I have a 0 value. So I know that my graph is going to look like this. So be really careful here. This one is going to be when theta equals pi over 2. Down here is when theta equals 3 pi over 2. My theta interval is 2 pi, 2 times the integral from pi over 2, 3 pi over 2, and then plug in our 1/2 r squared d theta. Again, I'll leave this to you to finish off, and the answer is going to be the same as above, 6 pi square units. Now here's a different kind of question. I want to find the area inside the smaller loop of the limacon. R equals to 1 plus 2 cosine theta. When theta is 0, we get 3. When theta is pi, we get -1. So notice angle is pi, but I have -1. That means somehow it has gone around and done this. This is 0 to pi, and then the remainder of it looks like this. So we need to know when r equals to 0. 0 equals to 1 plus 2 cosine theta, so that means cosine theta equals -1/2. Theta equals to 2 pi over 3 or 4 pi over 3. So we can set up our area as 2 times the integral from 2 pi over 3 to pi of 1/2 r squared. This is going to work out nicely. You'll have another cosine squared to deal with and power reduce that. So example 4, I want us to find the area shared by the circle r equals to sine theta and the limazone r equals to 1 plus cosine theta. Circle r equals to sine theta. It's symmetric left and right because it only has the first order of sines. This particular graph has a theta interval of 0 to pi. So what's happening is your circle is going around this way. What about 1 plus cosine theta? And it's actually going to cross around when theta equals pi over 2, we have 0. So it's 1, so I know it's actually going to cross right here. So I want the area of the region shared by the two. Look at this section just in here. That section is a semicircle. It is half of a circle with radius 1. 1/2 of 1 squared. It'll be 1/2 pi. Could we have set that up as an integral? Sure. That would be the integral from 0 to pi over 2 of 1/2 r squared d theta. Now I need to find the area of region 2. Everything in quadrant 2 only depends on the limazone. The red curve, my circle, does not actually form the boundary for that. So I can set this up as the area equals to the integral from pi over 2 to pi of 1/2 r squared d theta. So add them together and that'll give you the area of everything. If you are unsure that the two meet right here, we can actually calculate that, and I'll just show you really quick how you would do that. If you needed to find intersections of two graphs, you would set them equal to each other, and actually in this case it's a little more involved. Okay, so for this particular problem, not totally necessary because we can actually calculate at pi over 2 that they are there in the same spot, but this actually still is a good demonstration for you guys on how to solve this equation. Okay, and then you would find in this case theta equals pi over 2, 3 pi over 2, and pi. Now 3 pi over 2 would be outside of our domain because our circle only goes from 0 to pi, so they do intersect in these two spots, pi over 2 and pi. Well, we've got one last example. I want us to find the area in quadrant 1 only of the region outside the circle, but inside the limazone in example 4. That'll be all of this in quadrant 1 only. If we're trying to calculate the area, because we're rotating around the pole, it's going to be further from the pole minus closer. So kind of like outside minus inside. So we can set this up as 0 to pi over 2, and the outside is going to be our blue, which is the limazone. So 1/2 r squared d theta minus the inside. So 0 to pi over 2, and we're subtracting this part. All of quadrant 1 minus the purple will give you the orange. Okay, so this region minus this region. Okay, so 1/2 sine squared theta d theta. And evaluate that integral, and that'll give you the area inside the limazone, but outside the circle.